Class, we have discussed about the different types of columns. Main columns, particularly, it could be analytical or preparative. Apart from the main column, you also have pre-column and guard column. Pre-column is mainly for purifying the solvent system, that is the mobile phase, because there could be some dissolved impurities which would have gone through the filtration and degassing procedures. So it is still there and it can damage the column. So to remove such type of impurities, we use a pre-column. And we have seen what it is, so I will not go through it again. A guard column, on the other hand, is placed after the sample injection port, but before the analytical column. So it's very clear it is to purify any dissolved impurities in the sample which could damage your analytical column. So these were the other subsidiary columns. We have the main column, which could be analytical or preparative, or even semi-preparative. These were the three different types of columns which we discussed last time. The main differences are in the dimensions and the particle size of the stationary phase that is loaded. Today we'll go forward how to choose or what is the criteria to choose the packing materials. So these are the number of criteria which actually help in deciding which packing material to be used in an HPLC column for a given separation. It could be based on the particle size, the surface area, the particle shape, then bonding type, pore size, and carbon load. So we will go through each one of this in detail, what it refers to, starting with the particle shape. So, which is the best type of particle shape? It is spherical particles. Why spherical particles? Because they offer reduced back pressure and longer column life. What is back pressure? It means the column is exerting some pressure in the opposite direction to the flow of the mobile phase. What happens then is the mobile phase pressure and its flow rate will get affected if the back pressure of the column is becoming more and more. So always back pressure should be quite low so that the pressure and the flow rate of the mobile phase does not get affected. We will be getting what we have set it to be. So this is best happening when you have spherical particles being loaded in your HPLC column. Why so? Now see, this is an irregular shaped particle. This is a spherical particle. Now when you put two, three, four spherical particles around this, you will see there will be uniform sized pores in between the spherical particles. But if you have an irregular particle, a number of irregular particles. The second irregular particle can fit in properly in this gap. The third can fit in this gap. And therefore, the pores in between the particles will be missing. What is the effect of such an event? What will happen is the mobile phase will be obstructed. The flow rate of the mobile phase will be greatly affected. And that's why we say always spherical particles are best. For any chromatography, spherical particles would always be the best option. Next, we see the particle size. Other parameters was the particle size. Smaller particle size offers higher efficiency, but also cause higher back pressure. Choose 3 micrometer particles for resolving complex multi-component samples. Otherwise, choose 5 or 10 micrometer particle size. Something related here. If this is 10, this is half the size is 5, and approximately a little over half the size is 3 micrometers. Now here we have seen smaller particles offer higher efficiency. Why? Higher efficiency means better separation. Why? Because smaller particles have larger surface area. Larger the surface area, more the chances of easily getting absorbed. For what to get absorbed? The sample. Sample can easily get absorbed at a given point. It need not travel lower down the column and then get absorbed. because there was no space. So space is abundantly available and therefore easy absorption is possible. But it also causes high back pressure. Why? I think you know, smaller the particles, the pores between the particles become smaller, and therefore this restricts the flow of the mobile phase at a given pressure. If the back pressure is not high enough, you always go for smaller particle sizes. So that's why it's given here. 3 micrometer particles are used only for resolving complex multi-component samples. If you have a sample mixture that has got very few components and they are very different in nature, polarity wise, then it would result in a very easy separation. For this, we don't need to go for very small particle size. Hence, you will not have the problem of column back pressure. It's easier to go for 5 micrometer particles. In such easy separations, we would never prefer 3 micrometer separation, 3 micrometer particle size for the stationary phase. We have also seen in the last class that the larger the particle size, the column becomes less expensive. So definitely that would be the preferred option. Next parameter which affects your choice is the surface area. So high surface area generally provides greater retention, capacity and resolution for separating complex multi-component samples. This I just told you in the previous, because more the surface area, more the components that can be absorbed within a given area. If the surface area for absorption is less because of larger particle size, then you will have fewer components which can be absorbed on the surface. So you will need larger amount of stationary phase, you will need more longer columns, where you will need longer analysis time. These are all not desirable features. So our aim would be always to increase the surface area, which can be done by having smaller particle size. So the next parameter is pore size. Larger pores allow larger solute molecules to be retained longer through maximum exposure to the surface area of the particles. When can you get larger pores? When the particle size is large. Okay, so we have to decide based on what type of solute molecules you have. If your solute molecule cannot enter the pores, then it will just get washed away with your mobile phase. There will be no separation. So if your solute has got large molecules, that is your sample has large molecular solutes, then you will have to provide larger pores. And for that, the particles will have to be larger to give you larger pores. Then only there will be maximum exposure to the surface area of the particles, and there could be a proper distribution occurring, and a distribution equilibrium is achieved within a shorter time. So choose a pore size of 150 angstrom or less for samples with molecular weight less or equal to 2000, whereas you choose a pore size of 300 angstrom or greater for samples with molecular weight greater than 2000. That means the large particles. For the large particles, we need to have a larger pore size. Next parameter is the bonding type. So you could have monomeric bonding or you could have polymeric bonding. Any one of these can be seen in the various columns. Monomeric bonding offers increased mass transfer rate, high column efficiency, and faster column equilibration. What it means is a single molecule bonding. So at a given bonding site, you have a single layer of the solute, single monomolecular layer of the solute getting absorbed. So this will actually help. Now we'll just see this part. See, this is bonding of the stationary phase. So you have the stationary phase, it is mixed with this seleniated silica, chloroseleniated silica is what we generally use, and you get a monomeric bonding. That means the final bonding site will be able to bond with a single solute molecule. And you have only one molecule of the bonding site, and so one molecule of your solute may bond to it. Now, if you have polymeric bonding, that means more sites are available, so it takes longer for the solute to get bonded because more solutes can bond at a given uh, part of the stationary phase. Polymeric bonding, therefore, offers increased column stability, particularly when highly aqueous mobile phases are used. Polymeric bonding also enables the column to accept higher sample loading because more of sample can be attached at a given within a given area because there are more bonding sites. In monomeric bonding, there is only one molecule or one bonding site available to bond with your sample. So, but since it is only one, faster equilibration is available. So, higher column efficiency will also be available to you. So, depending upon what is your requirement, you can go for monomeric or polymeric. Generally, we go for monomeric bonding. But if you have highly aqueous mobile phases, then you should prefer the polymeric bonding. And lastly, the carbon load. So, how does the carbon load affect your um, separation? So higher carbon loads generally offer greater resolution and longer runtime. What does carbon load mean? How many carbons are there in your stationary phase? Say, for example, in the reverse phase, you have C2 columns, you have C8 columns, you have C18 columns. Out of this, which has higher carbon load? C18, because there are 18 carbons. So carbon load is higher in C18 compared to C2 and C8. Higher carbon loads generally offer greater resolution and longer runtime. So the analysis will take longer, but the separation will be highly efficient. On the other hand, low carbon loads shorten runtimes and many show a different selectivity. So here, if your main aim is to make your analysis faster, complete it faster, then you go for shorter carbon loads. If you want very good resolution also, as well as short retention time, you take a compromise between the two and you go for medium carbon loads, which is the most commonly used for starting an experiment where you have an unknown sample. And you also will see about the packing material, so how it influences the resolution of your experiment and your separation. Silica-based materials, you have the silanol groups, SiOH, on the surface. So this OH, if it is present like this, then it will help to only bind the polar molecules to this. But if you want a reverse phase um, HPLC to be done, then you'll have to modify it. So silica can be altered by reaction with organochlorosilane or organoalkoxysilane to give SiOH it was earlier. Now after reacting with this, it becomes SiO-SiR linkages with the surface. So what does R stand for? For some organic group. The attachment of hydrocarbon chains to silica produces a non-polar surface suitable for reverse phase chromatography, in which mixtures of water and organic solvents are used as eluent, because you are going to use a mixture of water with a little organic solvent, but your stationary phase will be more non-polar. So attachment of hydrocarbon chains produces non-polar stationary phase. This is therefore useful for reverse phase chromatography, where the mobile phase will be more polar. The most popular material is octadecyl silica, ODS, which is in short always called the ODS column, which contains C18 chains. But materials with C1, C2, C4, C6, C8, and C22 chains are also available. The latest silica, all these of course would be the RPC columns or reverse phase chromatographic columns. The latest silica-based bonded phase to be introduced is a long C30 phase, which makes it one of the most retentive phases available. Because the more nonpolar, it will help to retain the organic solutes much longer. So normal phase packaging material. So what could be used as stationary phase? When you have normal phase HPLC, the system consists of stationary phase, which would be more polar than the mobile phase. Easy way to remember is, say the stationary phase is polar, mobile phase is non-polar. This is strictly not true always because you may not have a completely non-polar mobile phase. The only necessity is that the mobile phase should be more nonpolar than the stationary phase and should not be miscible with it. Stationary phase in such normal phase chromatography is made up of either silica, alumina, or siloxane with polar functional groups like cyano, diol, amino, dimethylamino. We call these cyano columns, diol columns, or amino columns. So these type of, when you hear such names, these all refer to the normal phase column. And we are going to be doing a normal phase HPLC. The mobile phase in these columns in the normal phase chromatography would be more nonpolar. So it could be N-hexane, methylene chloride, chloroform, etc. So you all know these are the nonpolar mobile phases. They could also be mixtures. The unmodified silica is most widely used in HPLC, that is with the silanol groups, what I showed you in the first picture of the stationary phase. It has high efficiency and high permeability, which allow normal operating pressure less than 2000 psi to be used. It has also relatively higher surface area. It's good for normal phase chromatography. High HPLC grade silica consists of totally porous microparticles with spherical irregular shape and diameter 3, 5, 7, or 10 micrometer. So spherical or irregular shape, but spherical is the preferred shape. Irregular shape is not preferred. And diameters, it could be 3 micrometers, 5 micrometers, 7 micrometers, or 10 micrometers. Nowadays, 10 micrometers is very rarely used except in the preparative and the semi-preparative technique. We come to the reverse phase chromatography. The opposite arrangement of normal phase chromatography, that is stationary phase is nonpolar, mobile phase polar, is found in reverse phase. It's just the opposite. So you have a stationary phase that is more nonpolar than the mobile phase, or the mobile phase is more polar than the stationary phase. Stationary phase is made up of octadecyl, that means C18, or octyl, that is C8 chain, or butyl, that is C4, or even phenyl group. So these are the various types of stationary phases that you may come across in reverse phase columns. They are in short called the RP columns. Mobile phase would be more polar, so you will have methanol, acetonitrile, tetrahydrofuran, water, etc., and various mixtures of these in different proportions. So that completes about the column and the stationary phase. Now we come to another very important part of HPLC, that is detectors. So you can see a number of detectors listed here. We will not be dealing with all of them in detail. I've just put for your reference what are the possible detectors in HPLC instruments. Most commonly encountered one is the UV visible absorbance detector. So you will be studying the UV spectroscopy and the instrument UV spectrophotometer in very much detail in that chapter of spectroscopy. The same instrument would now be used as a detector for HPLC. Then it would be a UV visible detector. You can also have a photodiode array detector. This is same as UV visible detectors. It also provides UV spectra, but it is a number of these UV detectors all operating at different wavelengths at the same time. So these are all quite sensitive. So in the milligram, nanogram, microgram quantities, they can be easily used. Fluorescence detectors are much more sensitive, as you can see here. So the sensitivity becomes more and more in certain cases. However, refractive index will have a lower sensitivity. So whereas fluorimetry, because it is more sensitive method, it gives you higher sensitivity. Smaller quantities can be detected. So what is this fluorescence detector? In short, what type of compounds can be analyzed? Compounds with native fluorescence or with fluorescent tag. That means you make a derivative of that compound which is fluorescent. You can react it with a fluorimetric reagent and get a compound, a product that is fluorimetric. So then you can analyze with a fluorescence detector because it has the added advantage of higher sensitivity. Refractive index is actually universal indicator. It is also a bulk property indicator. What it means is that any type of compound, because every compound has its own refractive index, so based on the refractive index, it can be detected. So it can be, it's a universal detector, polymer, sugars, triglycerides, organic acids, excipients, not compatible with gradient analysis. This detector is not compatible with gradient analysis. Reason is, it's a, like I told you, it's a bulk property detector. So it will be recording the refractive index of the mobile phase, and whenever there is a change, it will show that a solute is getting eluted. If we use gradient analysis, then the refractive index of the mobile phase itself will be changing from time to time. And so correlating it with when a solute is getting eluted becomes more difficult. And then you have ELSD detector, that's evaporative light scattering device detector. This is also a universal detector. It is used for non-volatile or semi-volatile compounds compatible with gradient analysis showing high sensitivity. Corona charged aerosol. This we will not be. These are all more very specific detectors. It's a universal detector, but not used commonly because these are all very expensive detectors. So it is used only for specific analysis by specific labs dealing with such analysis. Then you have chemiluminescence, nitrogen electrochemical detectors, conductivity detectors, radioactivity detectors. Of course, you know it's very specific for radioactive labeled compounds. Conductivity means there should be ions, so specific to anions, cations. Electrochemical could be it is also very specific only to electroactive compounds, that is redox compounds only. Mass spectrometer, highly useful, very efficient detector, but makes HPLC more expensive. You could have a single mass spectrometer as the detector, or you could have tandem mass, MS detector. So both universal and specific, these detectors, they are all able to analyze almost all compounds. They can be made very specific also. Structural identification is possible, very sensitive, very specific. You can see here where it has gone. It has gone to the femtogram level, picogram, femtogram. Picogram means 10 raised to minus 12 and femtogram is 10 raised to minus 15 gram. So it's very small quantities which can be determined using these detectors. Then you also have the NMR as a detector in HPLC. It's also universal because all compounds can be determined for structural elucidation and confirmation. Here, of course, the sensitivity is not as high as for mass. It is milligram to nanogram quantity. So this is just a comparison of various types of detectors available. We will be dealing with most of them in detail. So now we can start with HPLC detectors. How they are classified based on their application. They are classified into two types: bulk property detectors and solute property detectors. Now, bulk property detectors compare an overall change in physical property of mobile phase with or without an eluting solute. Example, the refractive index detector. What this means, I'll tell in simpler sentences. This means that a bulk property detector would be able to detect the presence of the mobile phase as well as the presence of solute molecule that is getting eluted out. Now, when only mobile phase is traveling, then it will be giving a particular reading. And when any solute gets eluted, then based on the solute's property, it will give a different reading. So when there is a change in the reading, then you will be able to know that the solute is getting eluted out. So therefore, for this detector to be sensitive, you need a large difference in the physical property that you are measuring between the mobile phase and the eluting solute. Then the sensitivity will be high. If the two have got very similar physical properties, say refractive index detector, physical property measured is refractive index. If the refractive index of your solute and the mobile phase is very similar, then large amount of solute has to be eluted to give a difference and to detect the presence of the solute. That means you will have lower sensitivity. Sensitivity is greatly affected in an undesirable fashion. So we would require a large difference in refractive index between mobile phase and eluting solvent. Now, solute property detectors, on the other hand, they respond to physical property of the solute that is not exhibited by pure mobile phase. Example, UV visible detector, fluorescence detector. What this means is that physical property will be measured, which is not recorded for the mobile phase. So actually the response will be almost zero or no response when only mobile phase is coming to the detector. Whenever a solute gets eluted and arrives at the detector, then immediately it will respond. The detector will show a response because the solute that is getting eluted will be having a property that is being measured by the detector. I'll take the example of UV visible detector. Now, UV visible detector can detect compounds that are capable of absorbing UV radiation. So, the mobile phase will be one. We'll choose a wavelength at which the mobile phase will not be capable of absorbing UV radiation. Hence, the absorbance will be zero and you get a flat baseline. Whenever a component, say the first component is getting eluted, the component is capable of absorbing UV radiation and therefore when it is getting eluted, the detector will show some absorbance reading and you will get a peak in your chromatogram. This is how detection takes place in solute property detectors. So even if a small amount of solute gets eluted out, it will immediately be recorded. And that is why we say solute property detectors have got more sensitivity than bulk property detectors. Now, the characterization of detectors. What are the desirable features of detectors? The detector should have adequate sensitivity, should be capable of measuring very small amounts of solute so that Even if your sample has got very trace amounts of a given component, it can be recorded. Stability and reproducibility should be high for detectors. That means every time you're injecting the same solution containing the same component, you should get the same result. And the detector should give a stable response for each injection. Wide linear dynamic range means from a low concentration to a high concentration, the response should be very similar. Similar in the sense not same reading, but say for 2 microgram, it is giving a reading of 10. Then for 4 microgram, it should give a reading of 20. For 6 microgram, a reading of 30. Like this, there should be a proportional increase. So that is called a linear response over a wide range. Short response time. The detector should be capable of responding fast because in HPLC it is a continuous flow of the mobile phase or the LUN. As it passes through the detector, the response should be generated. So for the response to be generated that fast, immediately for each section of the mobile phase flowing through the detector. For it to be detected like that, the detector should respond very fast. As soon as it comes across a given section of mobile phase, it should produce its response. The minimum volume detected easily. Even if the volume is very low, it should be easily detected by the detector, for which the sensitivity should be high. Similarity in response towards all analyzed. So same type of response should be given whether a given component is present in sample 1 or sample 2. And it should be non-destructive of the sample. So the sample should be, once you recover the sample, it should be capable of being used for further studies. So it should not be changed in any way. Those are the desirable features. Now we see each of these detectors. UV visible, these are the detectors that we will be studying. UV visible detector, which could be a free type, fixed wavelength detector, variable wavelength detector, and diode array detector. As the name implies here, you will be using this detector at only one wavelength. So you will have a source in that detector, source of light, which will be giving radiation of only a particular wavelength. And a variable wavelength detector means we will be using a wavelength selector with that source, with a polychromatic source, and different wavelengths can be made to fall on the flow cell through which the mobile phase is traveling. That's called a variable wavelength detector. With this, we can measure at different wavelengths. Diode array detector is a series of these UV detectors, a series of them. Each one will be operating at a different wavelength. So what is the difference between these two? In this case, in a given instant, the sample will be subjected to analysis at different wavelengths. But in this, the sample will be subjected to analysis at a given wavelength only, and you will have, if you want to measure it at a different wavelength, you will have to change the wavelength and inject the sample again. That is the difference. Here it's a single wavelength which can be varied. Here it's a single wavelength which cannot be varied, and here it's multiple wavelengths in a given injection. Then will be studying the fluorescence detector, refractive index detector, ELSD, evaporative light scattering detector, electrical conductivity detector, and electrochemical detector. So the UV visible detectors most commonly used, like I mentioned earlier, the mobile phase from the column is passed through a flow cell. A flow cell would be something like a tube through which it will be passing, held in the radiation beam of UV visible spectrophotometers. So you will have the full UV visible spectrophotometer where you place the cuvette in there, where you place the sample holder. Instead of that, there will be a flow cell through which liquid will be continuously passing. That's why it's called a flow cell, not just a cell, because liquid will be continuously continuously passing. This minimizes extra column band broadening. Pressure less than 600 psi is required. That is why it's very common. We don't need very high pressure. And it is selective in nature to those compounds capable of absorbing UV radiation. Which are those compounds? It's the compounds which have either pi electrons or n electrons. So you know where pi electrons are present? In pi bonds. That means unsaturated compounds. Fixed wavelength detector is the first type. It operates at 254 nanometer. Higher detection capacity. These are its features. Mercury vapor lamp is used, and that's why the 254 nanometer wavelength is because one of its emission lines is at 254 nanometer. So measurement will be done only at this wavelength. Focus of light through two absorption cells. One will be the sample cell, the other is the reference flow cell, where only mobile phase will always be traveling. In the sample flow cell, it will be mobile phase sometimes or eluted solute component some other time. Volume of cell is always kept constant. Variable wavelength detectors, relatively wide band pass UV visible spectrophotometer is coupled to a chromatographic system here, offers a wide selection of UV and visible wavelengths with increased cost compared to the fixed one. For complete spectrum, LUN flow must be stopped to trap the components of interest in the detector cell, and use of phosphorus converter may be required. Diode array detector, scanning wavelength detector required to obtain a real-time spectrum of each solute as it elutes. Works in parallel, monitoring all wavelengths. So xenon lamp, because it gives wavelengths across UV visible radiation region of the spectrum. Then complete development of chromatogram in one injection is possible. This is how it looks. A number of these are put here. Diode array detector, so many individual, these are all individual detectors. And each of them is operating at a different wavelength, as indicated by the different colors here. So each one will be operating at a different wavelength. So each one responds, gives a response at a different wavelength. Then you have the fluorescence detector. This detects those materials which will fluoresce, or appropriate derivatization may be made to cause fluorescence. UV lamp provides the excitation radiation. Light is focused by the quartz lens through the cell, and another lens situated normal to incident light and focuses the fluorescent light on the photocell. You will be studying fluorimetry in detail. Basically, what happens in fluorimeters, which is used as a detector here, is UV radiation is used to excite your sample. The sample, if it is fluorescent, will emit fluorescent radiation. This fluorescent radiation is captured at right angles. So the light is focused by the quartz lens through the cell, and another lens situated normal to incident light focuses the fluorescent light on the photocell. This is how a fluorimeter, I am not sure whether you have got the picture here, but when you study fluorimeter, you will automatically be able to understand this, because need to explain a lot about fluorescence and the phenomenon of fluorescence for you to understand why it is placed normal, because what is emission, what is incidence, what is transmission, those are spectroscopic details that you need to know. This is the position. Here you have the source. This is the sample cell or the flow cell through which it is flowing. So the radiation falls on this. If the substance is fluorescent, it emits maximum radiation, fluorescent radiation in this direction. This is passing through a second grating. This is called the excitation grating, and this is the emission grating, and then reaches the detector, which shows a response. Refractive index detector is a universal detector or a bulk property detector. It is the least sensitive of the detectors that we are studying. Non-ionic compounds can be monitored well with this. Response to analytes changing the refractive index of the mobile phase. It requires a separate reference flow of mobile phase. Absorbance detectors are relatively cheap response to the deflection of light beam caused by differing refractive index. You know what is refractive index? It's refraction phenomenon. Light is deviated from its path, then we say it's refraction when it passes through a medium. So that principle is used here. So you have two compartments here. So this is the reference in, goes out. Well, what is reference? It's the mobile phase. This is your sample. Sample in and sample out. So this is your sample cell. So sometimes what happens in both of this, only mobile phase will be present. In that case, you will be getting some reading for the photo cell. Because both of these radiation path taken when refractive index of LUA changes. When will the refractive index of this change? When a component gets eluted. Because a part of the mobile phase will be replaced by the component that is getting eluted. The mixture of the eluted component and mobile phase will have a different refractive index compared to pure mobile phase. When that happens, the combination of these two refractions will result in a different path. So once you get here a different path, then the reading of this photocell will also be different. This is the original path taken when pure solvent is in both the compartments. That is only mobile phases coming out of the coming to the detector. Whenever a solute gets eluted, then the path will change because of the two refractions that is taking place in these two cells. Since the path is different, it will strike the photocell at a different angle, and therefore you will see the photocell responding differently to it. So the reading that is recorded will also be different. ELSD or evaporative light scattering detector is also universal. It is destructive. So this is not that desirable, but it is very useful being highly sensitive. The evaporative light scattering detector, as its name implies, utilizes a spray that continuously atomizes the column eluent into small droplets. So whatever is coming out, the eluate from the column will be atomized by a spray into small droplets. These droplets are allowed to evaporate. Okay, so the solvent that is present that will evaporate, leaving the solutes as fine particulate matter suspended in the atomizing gas. The reduction in light intensity detected due to scattering by the analysis method. So here in the fluorimetric, it was the fluorescence phenomena. In UV visible, it was absorbance being measured. And in this, it is scattering phenomena that will be measured. So when you have particulate matter and light is falling on a particle whose particle size is greater than the wavelength of radiation, then the light will be, if the particle size is smaller than the wavelength of radiation, then the light will be scattered. You get release scattering. So when it is scattered, the scattered light will ensure that the light that is transmitted, scattering is in different directions. So the light that is actually going through will decrease in intensity. You have 100 photons of light falling on the particles. The particles scatter, say, 10 photons, then remaining 90 will fall on the detector, and that gets recorded. So there will be a decrease in the intensity of light, depending on how many number of particles you have. More solute has got eluted, then more solute particles will be there, more scattering, lesser the depth. This is another picturization of the same. So you have the nebulizer gas eluent from the column. So here you will have the particles being formed, the droplets being formed, the droplets then evaporate, leaving the particles. And here you have the light falling on them. Scattering takes place. Whatever comes through that gets this is removed. That gets captured by a photocell. property detector consists of two electrodes. Bulk property, this is also a bulk property detector because the mobile phase can also give a response. It responds to electrolyte in mobile phase also. Most sensitive detector responds to substances that are oxidizable or reducible, and three electrodes are employed: working electrode, auxiliary electrode, reference electrode. If you have started with the conductometry chapter, then you will be knowing about these. These are the electrodes. We are not going to go into detail. It is conductance of the solution is measured here. So this is just a picturization of an HPLC instrument. Not necessarily it should look like this because there are different types of instruments. They look different from one another. It depends on the make, the model, etc. But all of them will be having solvent reservoirs. These are the solvent reservoirs. You have a degassing unit here. This is the solvent delivery system or the pump that is present. You can see the pumps here. Then you have the injector here. This is an automatic sampling unit. Then you have the columns being placed in an oven if temperature has to be maintained. And finally, you have the detectors. This is a complete picture of that.